Welcome to the Explainer. So today we're going to put on our detective hats, mathematical detective hats, that is. We are diving into a really classic physics problem about a falling particle. And instead of just taking the answer for granted, we're going to literally solve the question from scratch. Stick with me because doing this is going to uncover a wild little twist at the end. Okay, here's the core challenge we're dealing with. How do you map the exact path of a falling object when the air is actively fighting back? Think about it, right? When something drops in the real world, it doesn't just accelerate perfectly in a vacuum. The atmosphere pushes back. It messes with the trajectory. Now, I know it sounds like your standard run-of-the-mill classroom exercise, but we are setting out to genuinely solve the question step by agonizing step. Because, as you'll see, trusting your own process is sometimes infinitely better than just blindly trusting a textbook. All right, let's look at our very first clue here, the original problem statement. Our goal, find the displacement and velocity of a falling particle with a mass of m. It's falling freely under gravity, but, and here's the catch, it's moving through a medium that exerts a retarding force directly proportional to its velocity. Basically, the faster this thing falls, the harder the air shoves back. We also know it starts completely from rest. Seems simple enough, right? But to really get what's happening, we can't just skip ahead to the answer key. We've got to solve the question from the ground up. Now let's actually visualize this mid-air battle. On one side, we have gravity, labeled as F subscript g, and that's pulling our particles straight down the z-axis. Fighting directly against it, pushing straight up, is our retarding force, F subscript r. Honestly, this simple visual breakdown is our anchor. It's the absolute key to framing the math before we even touch an equation. The push and pull between these two opposing forces, that's what drives the entire calculation we're about to do. So, to crack this case and actually solve the question, we need a game plan. 3 simple steps. Step 1, we anchor ourselves with Newton's second law. Step 2, we meticulously isolate all those velocity variables onto one side. And step 3, the grand finale, integrating over time. Having this clear, structured approach is literally what keeps us grounded in reality and leaves zero room for assumptions. Let's actually walk through the handwritten math here. We kick things off with mass times acceleration. That's m times dvz over dt. And we set that equal to our net force. So gravity pushing down minus our upward resistive force. By shuffling things around to group those velocity variables together, we set up a beautiful integral. And listen, this next part is absolutely crucial. Because our particle starts from rest, we set our initial time and velocity bounds to 0. That grounds the whole equation. Then, following the rules of calculus, we apply the natural log to both sides, exponentiate to get rid of that log, and boom, we gracefully land on our true velocity equation. Now look really closely at what we just derived. Notice that negative exponent? It's negative a times t over m. Why is that such a big deal? Well, physically, it means literally everything. That tiny negative sign tells us the particle is not going to just accelerate forever. As time takes on, that exponential term gets smaller and smaller, which means the velocity levels off. It hits terminal velocity, all thanks to physical air resistance. It's just so cool when the math perfectly mirrors the real world. Okay, we've got our proven velocity formula locked in. Next up, total displacement. We need to figure out exactly how far this little particle has actually traveled over time. So we take that hard-earned velocity equation we just solved for, we set up the integral for displacement, which we'll just call z, and once again, we run the math starting from time 0. Here, you can really appreciate the rigorous calculus required for this. We plug in those zero-state starting boundaries. We carefully pull apart the constant terms from the time-dependent ones, and we just apply standard integration rules line by line to trace the exact trajectory. Integrating that exponential term spits out another factor of m over a, bringing us right to our final displacement function. Honestly, seeing it all laid out step by step like this is deeply satisfying, mostly because we know precisely where every single variable came from. So here we are. We have our solid mathematical proof. And because we took the time to actually sit down and solve the question completely on our own, we are perfectly positioned to spot a massive, shocking plot twist. Let's compare our undeniable evidence to the official answer published in the textbook. Just look at this side by side. On the left is the printed textbook, and on the right is our handwritten derivation. Do you see it? The textbook completely drops the negative sign in the exponent for the displacement equation. It literally prints a positive at m. I mean, In the physical world, a positive exponent there would imply impossible, never-ending exponential growth. It's saying our falling particle wouldn't hit terminal velocity, but would instead just accelerate into infinity, totally breaking the laws of physics. Meanwhile, on the right, our math shows the correct, real-world reality, with that negative sign safely where it belongs.
I love this. Right there at the bottom of the page, written plain as day, book has error. This meticulous student realized the officially published, highly trusted textbook was just flat out wrong. And why? Because they didn't just passively accept what was spoon-fed to them. Because they actually did the hard work to solve the question themselves, they caught a fundamental, physics-breaking typo that the editors completely missed.
So to close out our little investigation, let's look at the actual mathematically sound equations that properly map our falling particle. For velocity, it's v sub z equals mg over a times 1 minus e to the negative at over m. And for displacement, our z, notice it proudly features that intact correct negative exponent on the e term. It's a real victory for physics. These formulas actually respect the laws of nature, they account for terminal velocity perfectly, and they prove why mathematical rigor really matters. Which leaves us with a pretty provocative thought, doesn't it? What other established facts are just sitting quietly in your textbooks right now, waiting for you to prove them wrong? The next time you're handed a printed formula, are you just going to blindly accept it as the absolute truth? Or are you going to grab a pen, trust your own logic, and actually solve the question for yourself? Thanks for hanging out with me for this explainer. Keep analyzing, keep doing the math, and always trust the process.